Today I'm super excited to explore this lesson on similarity, so stick around and let's meet on the other side of the intro. Roll it! Before I get into what this lesson is all about, guys, please go ahead and give this video a like. So far you've been doing a splendid job at watching the content, but many of you are forgetting to give the video a like. Guys, remember, this is how you can help the channel to grow, as the YouTube algorithm isn't favorable to content that isn't getting enough likes. So go ahead and hit that thumbs up. It will be greatly appreciated. Now let's talk about today's lesson. This lesson will be presented in 3 sections. Section 1 will be on similar lengths, Section 2 on similar areas, and Section 3 on similar volumes. Each section will be uploaded separately to give you a clearer understanding of each concept. So let's begin with similar lengths. Similar shapes are defined as geometric figures that have the same shape but not necessarily the same size. So, for example, we could not compare a triangle with a rectangle. We have to compare 2 triangles, and also the triangles would have to either be 2 isosceles triangles, but we cannot compare an isosceles with a scalene triangle. So that's what we mean when we say they have to be the same shape but not necessarily the same size. Now, they are enlargements of each other using a scale factor. We're going to be defining what a scale factor is and also calculating them. Now, even though we say they are enlargements of each other, the shape could also be smaller because we could have a fractional scale factor as well, which would have reduced the shape. Now, all the corresponding angles in similar shapes are equal, and the corresponding lengths of all the sides must be in the same ratio. Very important to note that the angles within similar shapes are exactly the same size, as angles cannot change size. So when we're dealing with similar lengths, we're talking about enlarging the length of the shape, but the angles remain the same. And remember, for example, angles in a triangle add to 180 degrees. Therefore, we couldn't have angles adding to more than 180. So angles remain the same. So now we're going to define what is meant by the term scale factor. So when we talk about a scale factor, we're talking about the amount that each shape is enlarged or reduced by. Important here to note that every side of the shape is enlarged by the same scale factor. So when we're linking up corresponding sides, it is the same scale factor of enlargement that each side will share. Now let's have a look at these 2 shapes. So these 2 rectangles here, they are similar. So if you look at shape A, we can count the squares 1, 2 along, and 1, 2, 3, 4 for B. So if we check carefully, we could calculate how do we get from 2 to 4. So if we do 4 divided by 2, the scale factor that links them is 2. However, we could also go from shape B back to A. So this time we would need to do 2 divided by 4, and we could write it as 2 quarters, which can be simplified. 2 divided into itself goes once, and 2 into 4 goes 2. So if we're going from A to B, then we would be enlarging by scale factor 2. However, if we're going from B to A, it would be scale factor of 1/2. So the scale factor of enlargement from A to B is 2. And the scale factor of enlargement from B back to A is 1/2. So if we notice here as well, we have 90-degree angles in each of the shapes. So even though shape A is smaller than shape B, the angles are identical. They are all 90 degrees. So let's look at calculating our linear scale factors. So when we talk about linear scale factors, we're talking about the scale factor that links the lengths of the sides of the shape. Now, in our other lessons coming up, or in the other sections of this lesson, we're going to talk about area and volume as well, but linear scale factor is the scale factor that links the corresponding sides of our similar shapes. So let's consider shape A and shape B in this question. They are mathematically similar. Now we're asked in part A to calculate the scale factor from shape A to shape B. And in part B, we are asked to calculate the scale factor from B to A. Two different questions. So what we want to do is to find out, how do we get from 5? What is the multiplicative scale factor that gets us from 5 to 20? So we could do this algebraically or by the unitary method. So we know that 5 times by something gives us 20. So I'm going to write 5 times by, I'm going to call that something x. So 5 times x should get us to 20. So 5 times x gives us 5x. And 5x is equal to 20. So we just need to divide by 5 on both sides to find what x is. So 20 divided by 5 is 4. So the scale factor 5 times 4 is 20. We could also have done the unitary method, which is just to simply do the 20 here divided by 5, which gets us to 4. Now we'll find that depending on the question that we're doing, the algebraic method will come in quite necessarily important for you to use rather than the unitary method. Now we're asked to calculate the scale factor from B to A. So this time we would need to do 20 times by something, which I'm going to call x, should get me back to 5. So 20 times x is 20x. 20x is equal to 5. Now I need to make x the subject here, so I'm going to divide both sides by 20. So x then is equal to, I can simplify 5/20. 5 into itself goes once, and 5 into 20 goes 4. So therefore the scale factor that gets me from B back to A is 1/4. And we can see from B to A we are getting smaller. We could also have just written 5 divided by 20 and then write it as a fraction, also simplified to 1/4. Beautiful. So that's the easiest part, just to find what do we need to multiply one length by to get to the other, and that's called our linear scale factor. Beautiful. So now let's calculate some scale factors here. So shape A and B are mathematically similar, very important language there. So we're told that the length of A is 4 centimeters and the length of B is 9. So part A asks us to calculate the scale factor from A to B, and part B asks us to calculate the scale factor of B back to A. So for the first part, I'm going to do 4 times something, so I'm going to let that be x. So 4 times x is equal to 9. So 4x is equal to 9. I then divide both sides by 4, and so that cancels the x, and that is equal to 9/4, which we can leave just like that as a fractional value. Now for part B, we're going from B to A, so we're going this direction. So therefore 9 times by something should get us back to 4. So 9 times x is 9x, and 9x is equal to 4. I just need to divide both sides by 9. So therefore x is equal to 4 9s. So we can see that they are actually the reciprocal of each other. So that's the easiest part. We could also have put this in a decimal as well, but sometimes it's better to leave it as a fraction, particularly if it results in a recurring decimal, which means that that decimal goes on to infinity. Beautiful. So let's look at this other example. So We're given triangle A and triangle B. We're told they're similar, not drawn accurately, so we cannot measure the linear components. In part A, we're asked to write down the scale factor of enlargement from triangle A to triangle B. Now we have some calculations to do. For in part B, we're asked to work out the value of X. Part C, work out the value of Y. And part D, write down the size of angle Z. So first step, whether or not the question asks us, we have to find out the scale factor always. So scale factor, something times by 4 makes 20. I'm just going to do 20 divided by 4, and that's equal to 5. So the linear scale factor is equal to 5. Now that we've got that, we can find anything else the question asks us to do. So we're asked to work out the value of X. So X, find the matching side on shape A, which is 3. We know that 3 multiplied by the scale factor will get us X. So straight away, X is equal to 3 corresponding side multiplied by 5, which is my scale factor. So therefore, 3 times 5 gets me 15. So the answer, X is equal to 15 centimeters. Awesome. Now we're asked to work out the value of Y. So from here, we can see that we're going to get smaller. The corresponding side of 25 here is linked to Y. So this time we have to divide because we're getting smaller. So Y is equal to 25 divided by the scale factor, which is 5. So 25 divided by 5 gets me 5. So Y then is equal to 5 centimeters, and we can check. So put my 5 here. 5 times by 5 gives me 25. So I'm sure I am correct. Now, if you notice here, the language has changed in part D. It says write down, which means there's actually no calculation that we need to do. So remember, angles do not change. So therefore, the corresponding angle here to Z is 20 degrees. That means Z is also equal to 20 degrees. Very important to think about the language, write down. Awesome. So now we're going to do a few more questions. So here we're given shape A and B, again similar. We're asked to work out the value of X and also the value of Y for B and C, but remember, not every question will tell you straight away to write down the scale factor. That's something you've got to remember, you've got to do. But part A says write down the scale factor of enlargement from A to B. So I need to look for the two sides on both shapes that I've got. So I've got 9 here and I've got 6 here. So I'm going to do 9, so LSF, linear scale factor, is equal to 9 divided by 6. So you can just put that in your calculator in the interest of time. So 9 divided by 6, and that gets me 1.5. So my linear scale factor is 1.5. Now we're asked to work out the value of X. So this section, corresponding side is 12. So from 12 to X, I'm getting larger. So I need to multiply. So whenever I'm getting bigger, I need to multiply. So therefore, X is equal to 12 multiplied by 1.5. I could just easily put that in my calculator. However, I could also just take the opportunity to show you how to do this if this was a non-calculator paper. So to multiply by 1.5 simply means I've got one lot of 12, and 0.5 means I've got a half of 12. So half of 12 is 6. So add them together. 12 plus 6 gives me 18. So that's 18 centimeters. So to multiply by 1.5, you take one lot of the number, and then 0.5 means you take a half of the number and then add them together. So 12 times 1.5 gives me 18 centimeters. Now also, I want to work out the value of Y. I can see that 12 corresponds to Y, but I'm getting smaller. So therefore, y would be equal to, because I'm getting smaller, I now need to divide. So it's going to be 12 divided by my linear scale factor, which is 1.5. So an easy way to do this is we could do it fractionally, but for the interest of time, I'm just going to put it in my calculator. So 12 divided by 1.5 gets me to 8. So the answer is 8 centimeters. Now I can know if I'm correct. If my answer is smaller, then I'm more inclined to believe my answer is correct because I'm going from a large to a small shape. Amazing. Okay, so this time we're going to go to an example where we are asked to show that these rectangles are mathematically similar. So remember, we talked about if the shapes are similar, then the corresponding sides of each shape, when we find their scale factor, the scale factors have to be the same because each corresponding side must be enlarged by the same scale factor. Now here are the two rectangles given. We got 30, 60 for length and width, and 1.8 meter, very important here, and 90 centimeters. So meters and centimeters are not compatible at all, so we must convert. So first of all the three lengths here are already in centimeters, so it's important to just give 1.8 as centimeters as well. So 100 centimeters is equal to 1 meter. So to convert from my meters to centimeter, I need to do 1.8 multiplied by 100. So 1, 2, that will get me 180 centimeters. I'm just going to put that on my diagram. Now this question gives us a beautiful opportunity here to ensure that we know what are the corresponding sides. Now if you notice here, it is 30 that corresponds to 90, even though the orientation, one vertical, one horizontal. But if we should turn around or rotate the shape, we could see 90 and 30 are the two corresponding sides. Please don't be tricked by this. Now it is 60. I'm going to put double line here, and 180 that are the corresponding sides. So all we need to do now is to find the scale factor of each corresponding pair, and if they are the same, we know that these shapes are similar. However, if they're not the same, then they are not similar at all. So let's go. We're going to do scale factor. So we're going to do 90 divided by 30, and that gives us 3. So let's see if the other pair are also 3. So now we need to do 180 divided by 60. So 180 divided by 60 is also 3. Beautiful. So that means each side is enlarged, the corresponding side is enlarged by the same scale factor. So we're going to write enlarged by the same scale factor. You've got to conclude intelligently. It's the same scale factor. Therefore, this is a symbol for therefore similar. Beautiful. Do not just calculate and leave it. Answer intelligently. It's asking you to show. So you must conclude that both of them are enlarged by the same scale factor. Therefore, they are similar. Nice for you to experience that question. Awesome. So we're moving to this question that asks us to find the perimeter of the shape B. So we're given two shapes. We're told they're similar, not accurately drawn to scale, but we're asked to find the perimeter of the larger one. Notice we don't have a lot of measurement on the larger one, but because we know they are mathematically similar, we can find the area of the perimeter of the small shape and then use the scale factor to find the perimeter of the larger shape. Beautiful. Now also, if you look here, you'll see that there are two lengths on the small shape that are missing. So we must fill those in. Now, from the top of the shape to the bottom here is 7. And therefore, this length from the top here to the bottom is 4. So if we do 7 take away 4, it means the length from here to here has to be 3 centimeters. So 3 plus 4 will give us 7 all the way from the top to the bottom. Now, all the way across here is 8 centimeters, and all the way from the top here is 2. So if I do 8 take away 2, this length here is 6 centimeters. Amazing. So now I've got all the measurements on this shape. I can go ahead and find the perimeter, or I can find the scale factor first. I'm just going to go ahead and find the scale factor. So I know the side 8 here corresponds with the side 20. So the linear scale factor is equal to 20 divided by 8. I'll just put that in my calculator. So 20 divided by 8, and that gets me to 2.5. So I know the perimeter of the larger shape will be 2.5 larger than the smaller one. So let's go ahead, calculate the perimeter for A. So perimeter, I'm just going to write peri of A. Let's just add all the sides together. I've got 2 plus 3 plus 6 plus 4 plus 8 plus 7. It's going to put that all in my calculator. So 2 plus 3 plus 6 plus 4 plus 8 plus 7. And that gets me to 30. So I know that the perimeter, so peri of B, is going to be 2.5 times larger than 30. So all I need to do is to do 30 multiplied by 2.5. Again, opportunity here. So we need 2 lots of 30. 2 lots of 30 is equal to 60. And then I need a half of 30, which is 15. Add them together, 60 add 15 is 75. So the perimeter of shape B is 75 centimeters. A beautiful application of this would be, for example, an architect making a house. You've got to draw a plan because you couldn't draw an actual drawing of what the house is going to be. So what you've got to do is to do a scale drawing, and then when they're building the house, they've got to multiply it by a scale factor to get the actual house that they need to have. So guys, now it's time for our key takeaways. So at the beginning of the lesson, we defined similar shapes, and we said that similar shapes are geometric figures that have the same shape but not necessarily the same size. We also mentioned that each shape is an enlargement of each other by a scale factor. However, the shape could also be smaller than the original shape if the scale factor is fractional. Talked about the fact that the angles in each shape will be exactly the same, as angles do not change their sizes. Now, we talked about the fact that a scale factor, when we talk about scale factor, we're talking about the amount that each shape is enlarged or reduced by. And the linear scale factor only has to do with the lengths of the shapes that are involved. Now, I have included in the description of this video some independent practice questions for you, and also the answers so you could mark your work to see how well you've done. Now, remember that there is part 2 and 3 of this video where we talk about the area scale factor and the volume scale factor. So we're going to do similar area, similar volume, and you'll also get some additional questions on that. Now guys, I don't think you've got to the end of this video without liking it, but if it slipped you because you were so engaged, please make sure that you give this video a thumbs up to help the algorithm to share this with other viewers as well. And also make sure that you share and hit Hit the notification bell if you haven't done so yet, and also remember we are on TikTok. There's still lots of things there for you to revise as well. So as you get into your new term, we want to make sure that over the summer holidays we are still revising. Absolutely brilliant. Guys, thank you so much for engaging and investing in yourself. And until the next video is uploaded, thank you so much for watching.